In the vast majority of cases of designing an IIR filter through an indirect method, the bilinear transform is used. The general idea behind the bilinear transform is the desire to find a transform S equal to B of Z, such that the transfer function of the discrete time filter as a function of Z is achieved by taking the transfer function of the continuous time filter Hc of S and replace S with the bilinear transform B of Z. Unfortunately, there will never exist a perfect bilinear transform B of Z such that the two filters match perfectly, because the frequency response of the discrete time filter Hd of omega is periodic, and the frequency response of the continuous time filter Hc of omega is aperiodic. But a good approximation can be achieved with the bilinear transform B of Z equal to C times Z minus 1 divided by Z plus 1. To see the relationship between the frequency range of the continuous time filter and the frequency range of the discrete time filter when using the bilinear transform, we will first substitute S with J sigma and C with e to the power of j omega Ts. Here we have used sigma for the frequency range of the continuous time filter so that we don't mix it up with the real frequency of the discrete time filter omega. Then the bilinear transform yields that j sigma is equal to C times e to the power of j omega Ts minus 1 divided by e to the power of j omega Ts plus 1. This expression can be rewritten slightly such that the complex exponentials e to the power of j omega Ts half cancel out, and by Euler's formula the two remaining complex exponentials in the numerator are equal to j times 2 times the sine of omega Ts half, and the two complex exponentials in the denominator are equal to 2 cosine omega Ts half. This yields the final expression that the frequency of the continuous time filter sigma is equal to C times the tangents of the frequency of the discrete time filter omega times Ts divided by 2. Here we have illustrated this relationship in a graph for 3 different values of C. The tangent allows us to map the infinite range of frequencies sigma for a continuous time filter into a finite range of frequencies between minus pi divided by Ts and plus pi divided by Ts for the frequency of the discrete time filter omega. And since the tangent is a periodic function, the bilinear transform allows us to map an aperiodic frequency range with frequency sigma into the periodic frequency range omega of the discrete time filter. By choosing the parameter C appropriately, we can guarantee that the frequency response of the continuous time filter and the frequency response of the discrete time filter are exactly equivalent for one chosen frequency. Assume that the frequency responses of the discrete time and the continuous time filter should be exactly the same for a frequency omega star. Then we want to choose a parameter C such that omega star is equal to C times the tangent of omega star Ts divided by 2. Then C must be equal to omega star divided by the tangents of omega star Ts divided by 2. As an example, consider this transfer function of a first-order continuous time filter. We assume that we want to have a sampling period of 0.1 second, and the behavior of the continuous time and the discrete time filter should be exactly the same at the cutoff frequency. Hence, omega star is equal to 0.5 radians per second. The transfer function of the discrete time filter Hd of Z is then achieved by taking the transfer function of the continuous time filter Hc of S and replacing S with a bilinear transform, which gives that Hd of Z is equal to 1 divided by 2c Z minus 1 over Z plus 1 plus 1. A couple of reformulation steps then gives that Hd of Z is equal to 1 divided by 1 plus 2c times Z plus 1 divided by Z plus 1 minus 2c divided by 1 plus 2c, where the coefficient c is calculated using the formula that we have derived above. For omega star equal to 0.5 and Ts equal to 0.1, c is equal to 20. So that finally our discrete time filter has transfer function Hd of Z equal to 1 divided by 41 times Z plus 1 divided by Z minus 39 divided by 41. So that the discrete transfer function has a pole at 39 divided by 41, which is on the real axis inside the unit circle but quite close to 1 to ensure the passband of the filter, and a 0 at minus 1. So this is an example how a first-order continuous time low-pass filter is converted into a first-order discrete time low-pass filter using the bilinear transform.